Okay, we have a really interesting integral here. This one was sent to me by Sid. We've got the integral from 0 to inverse cosh of square root of 2, natural log cosh of x times hyperbolic cotangent of x dx. Okay, I already did one video on this, and my method was a pretty long method. I liked it, but it's going to be a lot longer than what we have here. For this, the method actually comes from Sid as well, which is a major shortcut on what I did. This is kind of a crazy shortcut, and it's going to save a lot of time, actually. Like, I don't usually say this, but a lot of times people will say one method's faster than another, and I don't really believe it just because it's a matter of taste. But in this case, I think this is way faster. In this case, I think the method's going to be much faster. So what we want to do on this is just multiply n by 4 times sinh of x over 4 sinh of x. The reason for this is because hyperbolic cotangent, I can rewrite this as cosh of x over sinh of x. And then this is going to help us when we multiply this stuff in here. But now when I multiply it in, we're going to do it kind of carefully. I'm going to break up this 4 and write it as 2 times 2. So that's going to allow me to multiply one of the 2's on the natural log over here. And then with what's left, we're going to have 2 sinh x cosh x right here. Now for this 4, I'll bring it out front as a constant. So we'll have 1/4 here, and then this will become sinh squared x. But for sinh squared x, we have an identity for that. It's just the cosh squared minus sinh squared equals 1. So I can write this as cosh squared x minus 1. And then one other thing we can do is I can take this 2, and with log properties, I can bring it into the exponent on the cosh here. So we can turn this thing into cosh squared. And what that'll do is set up a u substitution. I'll just substitute now on cosh squared. I think in the other video I substituted for cosh. It ended up being, like I said, that was a much longer way, although there's a couple different parts to it. But we'll do our u for just cosh squared. Go ahead and differentiate right here. Our du value is going to become 2 cosh x sinh x dx. But then our du value is exactly what we have right here. So I'll go ahead and substitute. We've got the 1/4 in front. Then evaluating the bounds, when you plug this in here, first cosh of cosh inverse, this is just going to be square root of 2. Then we square it, and this just becomes a 2. And then you plug a 0 in here, that's just going to be 1 squared, or just 1. This thing's going to be natural log of u. All this again is du, and it's all going to be over u minus 1. But then on this, let's just reverse the sign. Instead of writing it u minus 1, let's write it as 1 minus u and bring a minus out front. But then what we notice, this is exactly set up to use the Dilogarithm. We can just use a formula on this. The formula, the input on it's just going to be this right here. And so if the formula gives us Dilogarithm of 1 minus z, where this is the z, we're going to have Dilogarithm of 1 minus 2, or just minus 1. But this has a well-known value that I found in a previous video. This is just minus pi squared over 12. So all we need to do is just multiply this together, minus pi squared over 12 times minus 1/4. And for my final solution on this, we just get pi squared over 48, and that's it. So with that one shortcut, it definitely at least cut the time in half, but really it was more than that. In the other video, we ended up with 2 Dilogarithms. The other one was a little more complicated, so that was more time. But then also I had to put them back together, and we had to use identities. So it was just so much longer that way. It was still an educational journey, but if you're interested in speed, this is going to be the way. Okay, that's it for today. Thanks everyone for watching. Have a good day.